Okay. Good morning, everyone. It's a pleasure to introduce Professor Elaine Shi, who will give a talk on Streamlet, textbook Streamline blockchains. First, I would like to acknowledge the traditional owners of this land. In this case, I am sitting at Marshfield, New South Wales. I would also like to acknowledge Anne Louise Brown, Helge Janike, Regine Richel, and Surya Nepal for their help and support in organizing this cybersecurity Data 61 seminar series. Because this is going over Zoom, and so you can ask questions, because Elaine wants that you can ask questions during the talk, and so you can feel free to ask question if during the talk, and you keep yourself muted, but whenever you have some questions, you can unmute yourself and ask the questions at that point. Don't have to wait till the end. And you can keep your videos on, because Elaine would like to see that people are there rather than only some names. And then I would like Shushmita to introduce Professor Elaine Shi.
Hello, everyone. It's a pleasure to have Professor Elaine Shi with us today. And thanks, Elaine, for agreeing to talk even on a Sunday. So it's Sunday evening for Elaine. Professor Elaine Shi is an associate professor at Cornell University. And she has a broad range of research interests, which include cryptography, distributed systems, foundations of blockchains, and language-based security. And she's a versatile researcher with many seminal contributions. And she has written, she's a co-author of the first peer-reviewed paper in Bitcoin, and also the first peer-reviewed paper on smart contracts. She is the recipient of the Packard Fellowship, the Sloan Fellowship, the ONR-YIP Award, the NSF Career Award, and the NSA Best Scientific Security Award, and various Best Paper Awards in various top venues. Elaine has obtained her PhD from CMU, and before joining Cornell, she was an assistant professor of UMD. And we are going to listen to a very interesting talk in a very, very simplified fashion. And Elaine gives very, very wonderful talks and you can enjoy this talk and interact with her during this talk. Thanks, Elaine, and over to you.
Okay, thank you so much for the nice introduction. So yes, if you could you please keep the video on? And please do interrupt me whenever you have questions. You can also type it into the chat. I'll try to keep an eye out on the chat, but you know, the best way is just to unmute yourself and speak up. It'll help me, you know, stay awake. It's a little late here. Okay, I'll talk about Streamlet, a really simple consensus protocol. The protocol is like, you know, really, I can talk about it in 3 minutes, but I'm going to do a little bit of like storytelling, tell you about what's going on in the blockchain community, and, you know, to make it more fun. So what's a blockchain? You know, every decentralized cryptocurrency obviously needs a blockchain, right? So we have a set of nodes. Here we have Ethereum nodes, and they're trying to agree on a linearly ordered log of transactions. It's also called a public ledger. And there are two important security properties that we care about, namely consistency and liveness. Consistency says that all of the honest nodes must agree on the log. So your network could be a little faster than mine, and your log can grow a little faster. That's okay, but it has to be the case that my log is a prefix of yours, or yours a prefix of mine. And the second property is liveness. Essentially, if I buy coffee, I want to make sure my transaction is going to appear in every honest node's log fairly quickly. It's not like I want to wait forever for my coffee. Okay, so now if all of the nodes, they behave honestly, then the problem is kind of trivial. But what makes it really fascinating is when some of these nodes can be corrupt. Like they can have malware, they can be controlled by an adversary who's trying to subvert the consensus. And even under such adversarial scenarios, we want to make sure that the remaining set of honest nodes will nonetheless agree on the log. Okay, so blockchain is kind of a modern name. Like in the past, it was called state machine replication or consensus. But for this talk, all of these terms mean the same thing. So as I said, you know, blockchain actually is not a new problem. So I got interested in blockchain because of, you know, cryptocurrencies like Bitcoin. But in fact, blockchains have been around for more than 30 years. In fact, all these companies in Silicon Valley, essentially everyone deploys a blockchain protocol, like, you know, basically variants of PBFT and Paxos. And, you know, because everyone needs to replicate their computing infrastructure. And when you start to replicate things, consistency becomes an important challenge. Cryptocurrencies essentially made it possible for the first time to deploy consensus at a large scale, you know, involving thousands to millions of nodes. And that's, you know, one of the coolest things about cryptocurrencies. So let me talk a little bit about, you know, the history of cryptocurrencies, right? So we started with Bitcoin that used proof of work. And it turns out proof of work was like the key idea that enabled consensus in a permissionless environment. Essentially, anyone can join. It's completely open. But, you know, one problem with proof of work is that it's very wasteful and you know, the electricity consumed by Bitcoin was like, at some point was about the same as the electricity consumed by the entire country, Ireland. So it was quite astonishing. And because of this, many blockchain projects started to shift to proof of stake, right? So in proof of work, it's like, you know, every unit of hash power I have, I get to cast one vote. But whereas in proof of stake, every unit of cryptocurrency I hold in the system, I get proportional voting power. Okay, so the interesting thing about proof of stake is actually, if you look at how proof of stake protocols are constructed, they actually go back to our classical roots. They, in fact, rely on permissioned consensus. Like if you look at the system in any snapshot of time, the set of players who are participating in the consensus is well known, like their public keys are known. And essentially in proof of stake, the key idea is you want to kind of keep evolving the committee over time to reflect the, you know, the latest state distribution. So this is great, right? Now we can kind of rely on our 30 years of knowledge to build proof of stake protocols. But the intriguing thing is that when you look at all these blockchain projects, like everyone's trying to invent their own consensus protocol. So you might wonder why. You know, we have 30 years of work in the space, like why can't we just utilize one of these existing protocols? I mean, it turns out, I guess, all of these classical protocols, they're still, in some sense, too complicated. In fact, you may be aware that there has been years of work in trying to simplify consensus protocols like PBFT and Paxos. You know, there are papers like Paxos made moderately complex, Paxos made simple, the ABCDs of Paxos, Raft, and so on and so forth. Okay, so today I'm going to tell you an almost absurdly simple consensus protocol. It's called Streamlet. It's like, you know, essentially the most natural kind of protocol you can imagine. Like basically the most natural way to understand it is the correct way. And you know, we think of it as like a unified protocol that can be used both for teaching as well as for implementation. Okay, so before I talk about Streamlet, so first I want to say, you know, in general, there are a few approaches in which we can construct a blockchain protocol. The first approach is that we can essentially have sequential composition of Byzantine agreement. So Byzantine agreement is a one-shot consensus protocol. And this approach is often discussed in a more theoretical setting. Like in practice, the second approach is often preferred, essentially a direct blockchain construction, right? All of these classical protocols like PBFT and Paxos that actually get deployed in practice typically adopt the second approach. because like the second approach often allows you to perform more system level optimizations, right? If you do like sequential composition of single shot consensus, it's really hard to do cross instance optimization like pipelining. So Streamlet is also going to follow the direct blockchain construction paradigm. Okay, so as I said, I can tell you the protocol in 3 minutes, but I'm going to, like, this is a 45-minute talk. So I'll artificially introduce some twists and turns, right? So I'll start actually by talking about classical approaches like PBFT and Paxos. I'll talk about the nice side of these protocols. And when we get stuck, we can turn our attention to Streamlet. So throughout the talk, we are going to assume that all of these blocks are hashed together to form a hash chain. So essentially every block has a parent hash that uniquely binds to a prefix chain, assuming the hashes don't have collision. And then the block contains an epoch number that essentially is like a timestamp. And then it contains all the transactions you want to confirm, as well as any other application-specific data. So in this classical style protocol, we are going to assume like essentially the epoch numbers are incrementing in all of these blocks. Okay, so here's a really simple protocol, right? This is kind of the most natural idea you can think about. It's voting based. The guy in the center, Vitalik, he's called the leader or the proposer, and everyone else, they're voters. So some of these people can be corrupt, like in this picture, Loki is corrupt. I mean, of course, the leader can also be corrupt. Okay, so let's look at the first idea that comes to mind. So let's say the leader makes a proposal. In this case, he proposed the orange block. So this is like something that you're repeating every epoch, right? So in every epoch, you want to confirm a block, and it begins by the leader making a proposal, and then everyone's going to vote on the proposal, right? So in this case, the leader proposed an orange block. If you are honest, you cast an orange vote. So the vote is basically a signature on the block. If you are corrupt, like Loki is, you don't have to follow the honest protocol, right? In this case, Loki didn't vote for the orange block. He voted for like two other blue blocks, one dark blue and one light blue block. Okay, so now what? Now you wait. You wait until you collect enough votes on the same block. So in this case, we are counting 2/3 number of votes on the same block, right? So when many people have voted for the block, it gives me confidence because a lot of people believe that this should be the next block, and then I can confirm the block. So very simple idea. It's really natural. And throughout the talk, I will call a collection of 2/3 votes on the same block a notarization on the block. Okay. And a very important thing to remember about this protocol is that the honest nodes will vote uniquely in every epoch. So if I'm honest, I'll wait until the leader makes the first proposal. I'll vote on that proposal and only that proposal and nothing else. Okay, so with this in mind, we can actually prove consistency together. So consistency proof is really simple, right? So imagine there are 2/3 people who have voted for the blue block. So some people have seen the blue block notarized, and there are 2/3 people who voted for the orange block, right? So both blocks are notarized, and now we want to show that the blue block is actually the same as the orange block. And if we can show that, we have consistency. So how do we show that? We can consider the intersection of these two sets. Because there are only n people in total, right? Essentially, we know that the intersection must have size at least 1/3. And now, we didn't talk about the corruption budget, but now essentially assume the adversary doesn't control too many nodes. Let's say less than 1/3 of the people are corrupt. And this allows us to conclude that there is at least one honest node in the intersection. And now this honest node has voted for both the blue block and the orange block. And remember what I said about honest nodes, right? Honest nodes vote uniquely every epoch. And therefore, we can conclude because there's an honest node in the intersection that has voted for both, the only explanation is that the blue block is in fact the same as the orange block. Okay, so that's a really simple consistency proof. Any questions at this point? Okay, so this is very nice, right? So essentially we have a very simple protocol, propose vote, propose vote, propose vote. Whenever we hear 2/3 votes, which is a notarization, we can confirm.
So Elaine, I have a question.
Yes.
So in this case, why do we need this? So even if half of the slightly less than half of the nodes were corrupt, so there will be more than half of this in the not corrupt, right? And their intersection will have contains a non-empty one, right? So why do we allow at most up to 1/3? Why not go up all the way up to half n?
We need that not only the intersection is non-empty, we need that the intersection contains at least one honest node. So right now the intersection contains at least 1/3, but the number of corrupt nodes are less than 1/3, right? So we can conclude the intersection contains at least one honest node. If the intersection is full of corrupt nodes, then we cannot make this argument.
Okay, thanks.
Okay, yeah, that's a very nice question. Thanks. Okay. So we have proven together that as long as 2/3 of the voters are honest, we get consistency. Okay, so what about liveness? I mean, obviously, if the leader is online and honest, and it keeps making proposals in every epoch, then we are all good, right? We get liveness. However, if the leader, let's say, crashes, or the leader proposes different blocks to different people, and people start to vote differently, then we can never collect enough votes on any block. And in this case, liveness can stall. Okay. So, I mean, we want the protocol to have decentralized security, so we don't want liveness to have to depend on a single guy. And what we want is, to have both consistency and liveness under the 2/3 honest assumption. And how can we do that? Okay, so how do we achieve liveness? So this is where these classical protocols become very complicated, right? If you look at these classical protocols like PBFT, Paxos, and many different variants, like they actually have a similar structure. The normal path is pretty similar to what I said, right? It's voting based, it goes by propose vote, propose vote, propose vote. And when things are good, we just stay in this normal path. But when, let's say, the leader fails, or the leader becomes malicious, then liveness can halt, and then the system needs to go into a recovery path. And oftentimes the recovery path is called a view change. Like in PBFT, it's called a view change. And this recovery path is usually pretty complicated because, like, in the normal path, we only got consistency, we punted on liveness, but whereas in the recovery path, we really need to have both consistency and liveness at the same time. We can no longer, punt on one. So in some sense, like if you look at a system like this, right, most of the time it's running in the normal path, but most of the code is actually in the recovery path. And, that's where all the bugs are. And okay, so the holy grail is, can we achieve full consensus, getting both consistency and liveness, but as easily as a normal path? Essentially, can we have something just like propose vote, propose vote, propose vote, but get everything? Okay, so this is when we start to talk about Streamlet. Any questions at this point? Okay, so let me tell you a couple of tweaks to the protocol, and then you can get both consistency and liveness in a very simple paradigm. Okay, so this is just you've seen this before, right? Let me reiterate: the entire blockchain is chained together through hashes, right? So every block has a parent hash pointer. It contains the epoch number in which the block was agreed on, and then it contains a set of transactions. So we are going to assume every epoch is 1 second, just for simplicity. So as it will become clear later, actually consistency doesn't depend on any network timing assumption. No matter how badly the network is partitioned, we still get consistency. And this one second is actually for getting liveness. Like obviously when the network is partitioned, we cannot guarantee progress, but as long as the honest nodes can talk to each other, make a round trip within the second, we make progress, right? So basically when network conditions are good, we're going to guarantee liveness. Okay. So in the previous protocol, like one problem was, we stick to the same leader, and when the leader becomes faulty, we try to switch leader, through a view change or the recovery path. But in the new protocol, like leader switch or view change is like super easy, and it's so easy, in fact, that I'm just going to like allow leader switch in every round. So let's say in every, not in every round, in every epoch, right? So let's say in every epoch, which is 1 second, we can have a new proposer, right? So we can just take the hash function h, and we can hash the current epoch number I, and that's the leader of the epoch. We can support other leader rotation policies, but for simplicity, this one, we can start with this one essentially. Okay, so this is just some terminology. I'm going to use the term height to call refer to the position of the block in the chain. So previously we required that the chain have incrementing epoch numbers, but as I will explain in a little bit, so in this new protocol, we don't insist on the blocks, that the blocks be incrementing. As long as like the epoch numbers are strictly increasing, it's all fine, right? So the number contained in the block is going to be the epoch number. And the epoch number, in this case, the block with epoch number 8 is at the height 5. Okay, so that's just some terminology. And since the protocol is like so simple, I'm just going to tell you the protocol, and then we can kind of try to understand it together. So it's like really short. This is the whole protocol plus a finalization rule in the next slide. So in every epoch, you propose your vote, right? The epoch's proposer will assemble a new block extending the longest notarized chain so far, and they don't propose this new block. Okay, so what is notarized? I mean, it's still like, 2/3 signatures. And notarized chain is when every block is in the chain is notarized. So vote, and I'm going to wait until I receive the first proposal from this epoch's proposer, and I'll vote on it, provided that the proposed block extends from one of the longest notarized chains I've seen. So I will insist actually it extends from one of the longest notarized chains I've seen, because if the block is extending from a very short chain, that means like the proposer is likely dishonest, like he's throwing away a bunch of work in the middle. So I'm not going to vote for that block in this case. Okay, so very simple rule, and it's very natural. And the only thing to keep in mind is that previously we said when the block becomes...
So I have a question.
Yes.
So in the previous slide, when you say one of the longest notarized chain, so you have a threshold on the length of the chains, and if any of these notarized chain have length greater than that threshold, then you will extend it from that. That is the thing.
So notarized chain is if every block is notarized. So as I will explain in a little bit, potentially there can be forks, but once you notarize, once you finalize the block, there cannot be a fork at that position, at that height.
No, that is okay. What I am asking about the longest part. So what is your, so is there a length threshold beyond which if any of the notarized chain have that greater than that length, then you will take from that?
There's no, I don't understand the question. There's no threshold. Like
I mean, so the longest notarized chain is like in terms of the length, whatever at the, suppose the longest is say 10. So and there are maybe five longest chains. So you can take any one of them. Is that the thing?
Yes. Like if there are multiple chains of equal length, it can extend from any of them.
Okay.
So let's say I've seen 3 notarized chains, both have length 5, and in this case, it's okay if the proposed block extends from any of them. It just has to be one of the longest notarized chain.
Okay.
Okay, so this longest, just you're counting the number of blocks in the chain, right? So it's like the most natural meaning.
Okay.
Okay. Okay, so I mean, so the only thing we have to keep in mind is we have to be a little more patient. Like in the previous protocol, right? We finalize a block when it becomes notarized. But here, you know, we don't finalize when it's notarized. We have to be a little more patient. And what we are going to look for is a good pattern. And what is a good pattern? We are going to observe, do I see a notarized chain with 3 consecutive epoch numbers in adjacent blocks, right? So in this case, I do. Like I see 6, 7, 8. There are 3 adjacent blocks and they have consecutive epoch numbers. So in this case, it's a good pattern. And when this good pattern happens, I'm going to chop off the last block and call the entire prefix final. Like in this case, the entire prefix 167 becomes final. So final means it can never be undone later, and all the transactions contained in it can never be undone. And you know, if I'm a car dealer, it's safe for me to ship the car because the transaction will never be lost again. Okay. So that's the whole protocol. Like I'll try to explain it a little bit, but essentially, you know, it's propose vote, propose vote, propose vote, plus this somewhat magical finalization rule. And part of the magic is in this finalization rule. And that's why we can kind of, you know, streamline the view change into the propose vote, propose vote, propose vote cycle.
I have one question, Elaine.
Yes.
Why 3?
We are actually going to do consistency proof together. So maybe let's do the consistency proof together, and you'll see there are like tricks you can do to like make it 2. I mean, in some sense, in practice, whether it's like 2 or 3 is not the most important performance parameter. You can make the protocol slightly more complicated and the 3 will become 2, but like part of the goals we had was to just give the most simple and most natural protocol possible and to remove like as many quirks that are unnatural to our understanding as possible. So like that's why we, I think, you know, have this really simple and lean protocol. Okay. So I guess now maybe it's a good time to think about what's actually possible, right? So like I said, we cannot insist that the epoch numbers be incrementing, right? Oh, let me say something about this finalization rule. So what this finalization rule is also saying is the following. If I have finalized up till height h, in this case, it means that there can never be another notarized block at the same height. So like this orange block can never become notarized in this case. That's why it's safe for me to finalize the block 7. We are going to prove this together later. But if you think about it, essentially, if I can prove that there can never be another block notarized at this height h, then in fact, we can guarantee consistency. Like it's safe for me to finalize until the height h. Okay. So I guess maybe right now it's a good time to discuss a little bit before we actually do the proof, right? So the protocol is really simple. You know, if everyone were honest, like we should see 1, 2, 3, 4, 5, like the epoch numbers should be strictly incrementing 1 by 1. But we cannot insist on epoch numbers like strictly incrementing. We have to allow skipping epoch numbers because, you know, some leaders may not be around. Let's say the second proposer is not around. Then, you know, if we don't allow skipping epochs, we won't have liveness, right? So this is something we have to allow. But once we allow like the skipping epoch, forks can happen, right? So in this case, we see like the 6 and 7 are kind of at conflicting heights with 8 and 9. Like this scenario can happen. But as I said, if you have 3 consecutive 6, 7, 8, they're all notarized, then you can prove there can never be another notarized block at the height h. So we are going to prove this together. Any questions? I guess right now it's a good time to kind of discuss the protocol and get some intuition before we do the proof. If no questions, then we can do the proof together. The proof is also really simple. It's kind of like 2 lines or something.
May I ask a question?
Yes.
So I recall that for the leader election part, we use a hash function and the input is some I, right? And what is I? Is it the head or something?
Oh yeah, I guess maybe it was not clear. So I was actually the epoch number. So like the simplest idea is I'm going to take the epoch number. Right now it's in epoch I. I will hash the epoch number, and that gives me a random leader.
So in this way, the leader is kind of like predictable. Let's say if we know the epoch, and then we can know who is the leader. And in this way, if someone knows he is a leader in a specific round, and after that, he just keeps withholding the block. And according this leader election, it's kind of something like for every epoch, there can be only one valid leader, and nobody can propose any other block. Is that correct?
I'm going to assume it's static corruption. So like the corrupt nodes are chosen a priori before the hash function is chosen. So if like the hash function, if you think of it as a random oracle, essentially if you have like 2/3 honest, like with 2/3 probability, it's going to choose an honest leader. So we can, there are known techniques that can upgrade the security to adaptive corruption, but that's beyond the scope of this talk. Okay. If you ask me at the end of the talk, I'm happy to discuss some of these techniques regarding adaptive corruption. Okay?
Okay.
Okay, so now let's go over the consistency proof. So just help you recall what we want to prove. We have 6, 7, 8. They're consecutive. We finalize till the 7 block. We want to show this orange block at the same height as the 7 block can never get notarized. Okay, so in the proof, I'm just going to use concrete numbers 6, 7, 8, but the proof can be generalized to any, 3 consecutive epoch numbers. Okay. So first, I'm going to divide into 2 cases. And to do so, we are going to rely on the lemma we already proved in the beginning of the talk. So essentially, we are counting 2/3, right, as the notarization. And the consistency proof we did earlier guarantees that every epoch can have at most 1 block notarized. That's because every honest node votes uniquely in the block. And this actually means something, right? It means if there's an orange block, notarized at the same height as 7, that orange block cannot have the epoch numbers 6, 7, or 8 because those, have already been consumed. So now there are 2 cases. Case 1 is when the orange block has an epoch number greater than 8. Let's just say it's 9. I mean, if it's 10, the proof is the same. And case 2 is when this orange block has an epoch number smaller than 6. And let's just call it 5, because if it's like smaller than 5, the proof is the same as well. So now we're just going to prove each case, and the 2 cases, the proof is the same. We are going to first do proof case 1 together, so you'll get a sense of the proof, and then we are going to just, apply the same proof to case 2. Any questions about the 2 cases? Okay, so let's do case 1 first. Okay, so we know that the block 8 got notarized. And that means many nodes voted for the block 8 in epoch 8. And whenever I say many, I mean more than 1/3 honest nodes must have voted for a block 8, right? For it to be notarized, it has to have 2/3 votes. And because, the adversary controls less than 1/3, for the block to be notarized, it must be the case that more than 1/3 nodes have voted for it. So now let's think about the protocol. Right? The protocol says I'm not going to vote for block 8 unless 8 extends from one of my longest notarized chains. So it means when I voted for 8, 7 must already be notarized. So this means the many people who voted for 8 in epoch 8 must have seen 7 notarized in epoch 8. So now I want you to think of these honest nodes, right? If they have seen 7 notarized in epoch 8, will they actually vote for the orange block in epoch 9? They have seen 7 notarized in epoch 8. Are they going to vote for the orange block in epoch 9? Yes or no? So obviously the answer should be no, right? And why won't they vote for the block 9 in epoch 9? I mean, remember the voting rule, right? I will only vote for the block if it extends from one of the longest notarized chains I've seen. In this case, does 9 extend from one of the longest notarized chains I've seen in epoch 9? It cannot, right? It cannot, because by epoch 9, I've already seen 7 notarized. So 9 extends from 6, and it doesn't extend from one of the longest notarized chains I've seen. So I will essentially just refuse to vote for that block. And because all these honest people, right, more than 1/3 honest people, refuse to vote for it, think about how many votes it can gain. It cannot gain more than 2/3 votes if more than 1/3 honest people simply refuse to vote for it. So we conclude 9 cannot get notarized. And that's the proof. Any questions? Okay. So, I mean, we can do another example with the same proof. Maybe it helps a little bit. So essentially case 2. Case 2, we want to prove the same, right? We want to prove that essentially the block 5 cannot get notarized. Now we want to prove, we are going to assume the block 5 is notarized and we are going to reach a contradiction. So if 5 is notarized, then it must be that many people voted for 5 in epoch 5. And again, many means more than 1/3 honest nodes. And for these honest nodes to vote for block 5, it must be the case that they've seen 3 notarized in epoch 5. Because they're only going to vote for block 5 if it extends from the longest notarized, one of the longest notarized chains they have seen, right? So it says 3 must be notarized at that time. So if they have seen 3 notarized in epoch 5, now the question is, are they going to vote for the block 6 in epoch 6? Well, again, the answer is no, because by epoch 6, they've already seen 3 notarized, but 6 doesn't extend from, you know, any chain having the same or greater height than 3, right? 6 extends from a shorter chain, which is 1. So they're just going to refuse to vote for 6 in epoch 6, and therefore we conclude that 6 cannot get notarized. So we reach a contradiction. So essentially, you know, if 6, 7, 8 were 3 notarized blocks, we conclude that 5 cannot get notarized. Okay, so that is the consistency proof. And maybe, hopefully this clarifies a little why, you know, we need to count 3. And this is also like, yeah, so this finalization rule is like a kind of magic. It's why we can get this proposed vote style protocol, but, you know, have both consistency and liveness at the same time. Okay. So now it's actually a good time to reflect on what I said earlier. So I told you actually consistency doesn't rely on network timing. And now you can think about it. I mean, all you have to do is just like stare at the proof and, you know, check each line. And you'll notice that actually the proof doesn't depend on any network timing assumption. And even when the network can be arbitrarily partitioned, the partition is really long, the network conditions are really bad, it doesn't matter, consistency still holds. Okay, so now I will state the Liveness theorem. I won't have time to prove it in this talk. The proof is in our paper and also in a new textbook, which I'll show at the end. Okay, so Liveness says during a period of synchrony. So what is a period of synchrony? A period of synchrony is a period in which the network is good, right? Let's say the honest people can talk to each other, make a round trip within a single second, right? Which is the epoch length. Remember, the epoch length was 1 second. And if the network conditions are good, then whenever there are 5 consecutive epochs with honest proposers, the honest nodes finalized logs will grow. And not only so, they grow by honest blocks, and meaning blocks proposed by honest people. So therefore, you know, if I wanted to buy coffee and I send this transaction to the network, you know, when the honest nodes make a proposal, they'll include this transaction and the transaction will get confirmed whenever there are 5 consecutive epochs with honest proposers. So one question is, okay, why 5, right? I mean, because earlier when we had the finalization rule, like we were counting 3 consecutive, but now we are counting 5 consecutive. So I won't have time to do the proof, but essentially the intuition is if you have bad proposers, they can do some damage, and you need about 2 honest proposers to fix the damage that was essentially done earlier by corrupt proposers. And afterwards you enter a good state. And once you enter this good state, you just wait for 3 more honest proposers, and then you can have 3 consecutive notarized blocks in the chain with consecutive epoch numbers. And then you can finalize more blocks. Okay. So that's the Liveness theorem. I won't have time to prove it. Yeah.
I have a question. Can you go back to this? So Liveness theorem shows that during a period of synchrony, honest not finalized chain will grow whenever 5 consecutive epochs have honest proposers, right? So that means it will grow if there are 5 consecutive epochs. But is it always true that the precondition of this theorem will be satisfied and you will be able to always get 5 consecutive epochs where there are honest proposers?
If you choose leaders that are random, like with constant probability, 5 consecutive epochs will all be honest, because 2/3 of the nodes are honest. I mean, in fact, you can just pick the same leader and have it be the leader for 5 epochs. That also works. So okay. Like every time you pick a leader with 2/3 probability, you know, you'll have like you'll make progress.
Okay.
If you deploy the protocol in the proof of stake setting, the protocol should be incentive compatible, right? You should like incentivize honest behavior. So hopefully, you know, in the real world, when it's incentive compatible, everyone's going to, you know, behave honestly because that's the best response. Okay. So by the way, the protocol can also support other leader rotation policies. Like for simplicity, I use the random rotation, right? Because that's like conceptually the simplest, but you can also have like what's called a stability favoring policy, just like in PBFT and Paxos, right? You can stick with the same leader when things are good and kind of switch them out when things are bad. Like the reason why I picked the random leader rotation policy is because like the kind of best way to demonstrate that leader switch is so simple in the protocol, we can just do it in every epoch. Like it's completely streamlined into the same proposed vote paradigm. Okay, so another thing to note here is that the Liveness theorem does depend on network timing, right? We only get Liveness during periods of synchrony, which means only when network conditions are good, we make progress. But you know, that's kind of inherent because if everyone cannot talk to each other, no one can guarantee liveness, obviously. Okay. So this is actually a good time for me to mention, you know, this cool model called partially synchronous, right? So in fact, I haven't told you this this term all the time, but in fact, Streamlet is a partially synchronous protocol. And in a partially synchronous protocol, we are going to give the protocol a pre-configured parameter called delta, which is our best guess of the network delay in good conditions. So let's say we configure delta to be 1 second. And essentially we are guessing when the network conditions are good, people can talk to each other within 1 second. It's okay if in reality, you know, sometimes people cannot talk to each other within 1 second. That's not going to like harm consistency, because the protocol always has consistency no matter how long the actual network delay is and no matter how badly the network is partitioned. But essentially only when the network conditions do respect this delta can we have liveness. Okay, so also there's a well-known theorem that says in the partially synchronous setting, any protocol cannot tolerate more than 1/3 corruption. So essentially 1/3 is the tightest you can do in this model, and Streamlet essentially has optimal resilience. Okay, so I'm just going to wrap up. So essentially, we talked about Streamlet, right? It's a really simple consensus protocol. Like all it does is propose, vote, propose, vote, propose, vote. It's like really natural. Like the most natural interpretation is the correct interpretation. And one cool thing about this protocol, in comparison with classical protocols like PBFT and Paxos, it doesn't have a separate view change, right? Because in some sense, as we have seen, we can switch leader even every epoch, and the view change is kind of just seamlessly woven into this proposed vote paradigm. So this is in fact, it's not just a protocol, it's a family of protocols. Like it's a technique you can apply not just in the partially synchronous setting, but also in the synchronous setting, right? So in the synchronous setting, the consistency proof is also allowed to depend on network timing assumption. And if you allow that, we can tolerate more faults. So for example, here's essentially the same protocol with tweaked parameters, but we can prove it's secure in the synchronous setting under minority corruption. So essentially the same. And the only change is like previously 2/3 votes is notarized and now majority votes is notarized. And for finalization, previously we were counting 3, chopping off the last block, but now we are counting 6 and chopping off the trailing 5. And also, not only are we counting 6 consecutive, we also want to make sure that these 6 don't have conflicting notarization at the same height. So that gives a synchronous protocol that tolerates minority corruption. I won't do the proof. It's fairly similar to the 1/3 case. Okay, so essentially, read after me: propose, vote, propose, vote, propose, vote. Boom, boom, boom. Confirm, confirm, confirm. Don't finalize upon notarization. Be a little more patient. Look for 3 adjacent blocks with consecutive epoch numbers. Chop off last one and finalize the prefix. That's the protocol. And I want to mention, right, I mentioned this textbook. I have a preliminary draft online, distributedconsensus.net. It's easy to remember. So if you have any feedback, please let me know. The draft is still being continuously polished and updated online. So always check back for the latest version at this website. Thank you so much.
Yeah, thanks, Elaine, for giving such a nice talk. So I would ask if any of the participants have any questions.
I have a question, and it is something that was previously asked. I just want to confirm. So you mentioned that when you are choosing the leader, you are essentially using hash of I, where I is the epoch number, right?
Mm-hmm. Yeah.
So what is the adversarial model over here? For example, if I know the epoch number, I can guess who is going to be the next one, and then I can compromise that leader, and I can go on doing this. I think this is something I also mentioned. So
right now, like with this hash-based random rotation, like it's proven secure under static corruption, meaning the corrupt nodes are chosen a priori, and then the hash function is chosen. But there are ways to, like, standard techniques to upgrade the security to adaptive security. Like you can use a VRF, and for details, you can actually look at the Pala paper. Like the Pala paper at the end discusses how to get adaptive security. And there's also another way to make it, like in practice, often mildly adaptive is strong enough. So like, for instance, the Snow White paper discusses how to kind of take a statically secure protocol and make it mildly adaptive. Like in some sense, adaptive is also, it's like too strong and too weak in a decentralized blockchain setting. It's too strong in the sense that, like, the adversary, I cannot just, okay, look at your message and decide to corrupt you this very instant. It usually takes me some time to target you and corrupt you. It's too weak in the sense that, like, in the proof of stake setting, I can, you know, post a bribery smart contract and say, okay, if you know you're going to be the proposer, let's say at 10 o'clock tomorrow morning, you know, I'm going to pay you 500 Bitcoins to buy your secret key. So this is like, you know, corrupting people way ahead of time before they even send the message. So it's too weak in that sense. So that there's, I think there's a somewhat of a mismatch, like, you know, adaptive is a technically very interesting model, like in the crypto literature. So, but I think, you know, one really fascinating challenge for decentralized cryptocurrency is, like, oftentimes we find that these classical modeling techniques, they aren't a great fit for these realistic applications. So it forces us to, like, rethink the modeling and to try to, you know, understand how to model the incentive and game theory aspects of these, like, systems.
Thank you.